Going back to our analogy of investigating a crime scene, we're down to step 5 here, down to analyzing the evidence. Okay, we've done an autopsy and we've looked at the benthic data itself, but now what other evidence like water quality data, habitat data, can we correlate with that benthic data to help us identify what some of the stressors might be? So the first thing we may want to do, particularly looking at water quality data, is to look at the data by site. Okay, again, hopefully we've got multiple stations within the watershed, particularly if we have a TMDL project where we've got multiple TMDL listed streams, we'll definitely have multiple stations. And hopefully, as we talked on Monday, hopefully we'll have a few within there that have good healthy benthics, some within watershed reference stations. If not, maybe we have a nearby regional reference station. And we'd like to look at and compare those stations by site for each parameter that we're investigating. Now keep in mind, as we're investigating the water quality parameters, going back to our discussion of tolerances, we're going to have to look at each one individually, although some of them interact. A box plot is a great way to do that. I would encourage you to produce box plots. Excel used to not be able to do box plots. The newer versions of Excel can. It's a little bit awkward. And so there's an optional homework for today, giving you some experience of making box plots within Excel. There's probably some other software that can do it perhaps a little bit better than Excel, but I know most of us are comfortable in working in Excel. So it's kind of odd. You have to arrange the data in a certain way in order to get a box plot out of it. The box plots typically will show the spread of the data. That's the point of the box plot. Typically, it'll show an average and a median, as well as an interquartile range. So this represents the 25th percentile of data and the 75th percentile of data. Okay, so within that box, that's where most of the results lie. And then you also have maximum and minimum values represented by the error bars, and outliers will usually be presented as a star. Those are determined as values that lie greater than 1.5 times that interquartile range. So based on how much spread there is between the 25th and 75th percentile, that will determine how far an outlier has to be outside of that before it's considered an outlier. So this figure on the right shows this was some data from, looks like the North Fork Rivanna River TMDL of a number of different sites, and you can see the different ranges and spreads as well as the averages of each of those sites. Next thing you might want to do is compare. Now that you have data analyzed by site, you might want to compare with that reference. Again, this could be a within watershed reference, or maybe a regional reference that's near the TMDL watershed that you're dealing with. And you can do statistical comparisons between that particular reference location and each of your TMDL stations. In this particular example, we had a reference station here. We're looking at dissolved oxygen, and this particular station, the D there indicates the statistically significant difference between dissolved oxygen at that station versus the reference. I will add a little bit of caution here with those statistical comparisons. Be careful of small data sets. Obviously, if you have a very small data set, you're probably not going to see any type of statistical difference in a hypothesis test just because there's not enough data. That doesn't mean that there is no difference there. That's just that there wasn't enough data to determine whether that difference was significant or not. And then also with small data sets, another issue you could have, particularly with things like dissolved oxygen, is when was the data collected? If you have a majority of data collected in the wintertime at one site, and maybe more data collected during the summertime at another site, you're going to see some differences in that dissolved oxygen data just based on the timing of those collections. And that may not necessarily indicate a true difference between those sites. So I think statistical comparison can be a tool for us. I wouldn't use it as a definitive yes or no in terms of whether something is a stressor or is not, because oftentimes there are other temporal differences, as well as maybe some small data set issues that come into play with those statistical comparisons. So use it as a tool, but along with other tools as well. Next thing we might want to look at is comparison to standards, water quality standards. Now, we may not have water quality standards for every parameter, but for those that we do, we definitely want to compare what we see at different stations with those standards. Okay. A couple other cautions here as well. Be aware that violations of a standard might not necessarily be needed to alter benthic community structure. Okay. Again, I know that probably makes some assessors uncomfortable. But for example, the dissolved oxygen standard was developed mostly to protect early life stage of fish. And most of the data that went into EPA's recommended dissolved oxygen standards, most of that information was from fish. Very little information from invertebrates was included. But even if you go back and you look at the original standards criteria documents, they do have some benthic macroinvertebrate data in there. And what that data actually shows is that many of the invertebrates have much more stringent dissolved oxygen tolerance levels than the fish do. Some of the stoneflies had tolerance levels as high as maybe 7 milligrams per liter as a lower dissolved oxygen threshold. So what does that mean? That means that we may begin to lose stonefly and maybe some other sensitive species as dissolved oxygen levels begin to decrease, even below 7 milligrams per liter. While our standard, we don't reach until we get to 5 or 4 milligrams per liter. So keep that in mind as well. Another great comparison is to compare values that we see at different sites with probability thresholds. DEQ did a great job of coming up with and publishing in 2017 the stressor analysis document, as well as the benthic stressor analysis tool that goes along with it. And the folks from BRO are gonna share some more information about that with you today, and hopefully maybe answer some of your questions that you might have with it as well. Some of you have probably already had an opportunity to use that tool. Others maybe you haven't, but you're interested in using it. It is a great tool to compare individual data at a station with basically statewide data. So what was done in the tool, and the folks from BRO can explain this better than I can, but what was done is we looked at statewide data. I believe it's from ProbMon data, and then looked at what levels of different parameters were associated with impaired benthic communities in those particular streams. Okay. I will give a little caution here again that the benthic stressor analysis is a tool. It's a tool to be used in benthic stressor analysis. It is not the stressor analysis. I think saying, oh, I ran the tool, I did the benthic stressor analysis is not accurate. I think it's one piece of a larger puzzle that will give you a tool of one way to analyze the data. I think we need to look at it in the context of other lines of evidence as well. Another caveat is that it's based on correlative data, not necessarily causal relationships. And so that's another reason why I think we need to use it within the context of other lines of evidence that support or refute a particular stressor. Another way we want to look at and evaluate data is over time. How do levels of individual parameters change over time? Do we have any increasing or decreasing trends of that water quality parameter over time? And how do those trends correlate with benthic data? Now, we talked about on Monday looking at the temporal trends within benthic data. And if we see increasing or decreasing trends in the benthic data, is that associated with trends in any one of the parameters, water quality parameters that we're looking at? If so, that might be an indicator that that particular parameter might be a stressor. If it is a stressor and we see the stressor levels going down over time, we should see benthic health improving over time. And obviously the vice versa is true as well. So as well as temporal trends, do we see any seasonal trends? What trends do we see in water quality throughout the seasons? Now, some water quality parameters will have distinct seasonal trends. Temperature, obviously, dissolved oxygen, both are going to naturally have seasonal trends. Well, do those seasonal trends correlate with trends that we see in the benthic data as well? We have fall and we have spring, fall and spring benthic data. Well, what do the levels of individual parameters look like in late summer leading into fall and in the winter leading into spring? Because those conditions will influence what the benthic health and benthic scores will tell you in that particular season. We also want to look at what's the timing of extreme values. Okay, maybe it's one of those outliers, or in this case, here's a graph from Swift Creek in the James River tributaries, TMDL, that we're working on in Piedmont office. And this particular stream, Swift Creek, dissolved oxygen gets very low. And when does that happen? Well, that typically occurs in the late summer and early fall. And we can even see in 2019 that it extended quite a ways into the fall, even through October. And again, how does the timing of those extreme values, how does that timing correlate with what we see in the benthic population? Also, notice that given a single toxic event, let's say, looking at our stress responses, if we have a lethal event that's going to kill some organisms, that will have an impact on benthic health for months after that. Because obviously, if you kill those organisms at that time, they're not going to be there the next day when you sample. But also, it's going to take a while for their communities to reestablish, even if that particular stressor is gone. Benthic macrovertebrates don't move around very well. And so their only way for recolonization is two things. One is drift from upstream to downstream. So again, as organisms, either they get flushed off of the rocks that they're hiding in and around, which could happen during higher flows, or if they're under some stress, they may let go of where they are and drift downstream. So that's one way of recolonizing. The other way is, as most of these benthic macrovertebrates, they're in the larval form, and as they grow to adults, they will hatch out, and most of them are flying insects. And so then, obviously, once you can fly, you can move upstream. If you're a stream-dwelling creature that only has tiny little legs and you don't swim very well, you can basically only go downstream. But the adults, they can fly to new areas, redeposit eggs at an upstream location, and then rejuvenate that particular population. But both of those mechanisms take time. And so you're typically looking at on the order of months before a population is reestablished after some given toxic event. All right, in evaluating water quality data, we also want to look at diurnal comparisons. If we have diurnal data that was collected, and again, I would encourage that if we have temperature or dissolved oxygen or pH that are suspected candidate stressors, because definitely the three of those parameters will change greatly throughout the cycle of a day. The diurnal monitoring can also sometimes be useful for even for sediment, because if you're monitoring turbidity, and if you have storm events during that time period, maybe the 1 or the 2 weeks while the sonde is deployed, that can give you a good idea as to what type of sediment conditions are you seeing during and following storm events. Even in pristine conditions, you will likely have increased turbidity levels during a storm event, but how quickly do they return to normal afterwards? That can sometimes be an indication of the level of sediment enrichment within a watershed. Looking at these three parameters, temperature, dissolved oxygen, and pH, all three of them will have natural daily cycles. Obviously, temperature is going to go up during the day and down at night. But that's actually primarily driven by sunlight. And it's actually driven less by the temperature of the atmosphere. For instance, if you're in the summertime and you've got a day, maybe it's a little cooler, maybe it's a day in the 70s, but you've got very bright sunlight, you might actually see higher temperatures in the day than a 90-degree day that's very cloudy. And so solar heating is very important for driving stream temperatures, as well as shading, having a riparian vegetation, a riparian cover that shades the stream, whether that's present or not, that has a huge impact on stream temperatures, as well as depth. Depth in the stream. The more shallow the stream is, the more quickly it's going to heat from solar heating. And the deeper, obviously, it's going to have a less of an impact because the solar incidence is on the surface. Also, sediment. Increases in sediment can also drive increasing temperatures during the daytime, because as the sunlight hits the water, the sediment gives the sunlight something to hit and scatter, and it will actually warm that particle more than clear water itself. For dissolved oxygen, we have natural daily cycles of dissolved oxygen going up during the daytime and going down at night. Now, that's a natural cycle. First of all, it's going to be driven slightly by temperature, but mostly it's going to be driven by photosynthesis. So whatever algae and periphyton is in the stream, that's going to be photosynthesizing during the daytime. And as it's photosynthesizing, it's going to be producing oxygen. And then at nighttime, as it's respiring, as well as all of the other heterotrophs, all the other organisms in the water, they're going to be respiring at night as well. That's going to be using oxygen. So we're providing oxygen to the water during the day from algae. We're consuming it. All organisms are consuming it at night. And that's going to drive those daily highs in DO during the day and lows in DO at night. Again, the reason we want to do diurnal measurements, particularly for dissolved oxygen, is because most of our periodic measurements where water quality samplers are out collecting is during the daytime. And so we never see what those nighttime levels are unless we're doing a diurnal comparison. And then lastly, for pH, pH has natural daily cycles as well. In this case, they're also driven by algae. As algae is photosynthesizing during the day, as well as giving off oxygen, they're also taking in carbon dioxide. And carbon dioxide dissolved in water is a weak acid. So during the day, as they're taking in a weak acid, they're removing acids from the water, basically making the pH go up. And then at nighttime, again, when they're respiring, CO2 is being given off. Again, it's a weak acid, so that's going to drive the pH lower. So if pH is of particular interest to us and is a candidate stressor, we might want to look at diurnal sampling as well to see, during the nighttime, how low do pHs get? Some other considerations for that diurnal sampling. Again, we want to try to target those critical times, those critical conditions, which are usually in the summer when temperatures are high and flows are low. We also, again, we're going to primarily be looking for the lowest dips are going to be just before dawn. I mentioned before, stream depth and shading are important. And then also the magnitude of the swings from day to night, particularly in dissolved oxygen, is one of the things that we might be looking for. We're going to be looking for both how low does it get and how does that compare with stressor threshold probabilities? How low does it get compared to our water quality standard? But also, what's the magnitude of the swings from daytime to nighttime? Because that could be an indicator of nutrient enrichment. So here's some data, and this is, I believe this is actual data from the current, from NESHA's TMDL project in the South Fork Rivanna, and some good examples of some very high and large dissolved oxygen swings from day to nighttime. In the top right, that's the South Fork Rivanna River, and we see in the daytime, sometimes we're up over 120% saturation. So again, looking at dissolved oxygen saturation is probably the best way to look at these swings because it's in comparison with how much oxygen water should hold at the given temperature. In this case, in the South Fork Rivanna, during most days in the summertime, there's actually more dissolved oxygen in the water than should be there, given the temperature, which means algae are definitely photosynthesizing and producing that extra oxygen. Now, the flip side of that is that at nighttime, you're probably going to get lower swings. And so in this case, it's swinging almost 60% from daytime to nighttime. I would say that if you have percent saturations during the day over 120%, that's probably an indicator of nutrient enrichment. And if you have swings from daytime to nighttime that are more than 40%, that's probably an indicator of nutrient enrichment as well. On the bottom there is Meacham's River, and that's probably a more typical stream signature for dissolved oxygen during the day, day to night, that would not indicate nutrient enrichment. You know, we're seeing maybe a little bit of supersaturation during the day, up over 100% occasionally, maybe as high as 110%, but it's not up in the 120% range. And then at nighttime, it's dropping, you know, to 90%, probably not even as far down as 80%. So two different examples there of where you might suspect nutrient enrichment. All right, so that moves us from evaluating water quality data now to take a look at how do we evaluate some of the habitat data. Okay, and really it's going to be many of the same approaches. The first one is, can we compare it to a reference? Our biologists, when they go out and collect benthic samples, they're also doing a habitat assessment at the same time. That information is available to us, and we can collect it. A lot of times we want to look first just at total habitat scores. So obviously there are 10 different metrics within that habitat assessment, and then we can add up those scores to look at total habitat scores. But then later we'll also look at the individual metrics themselves. For total habitat scores, we can obviously compare across sites, and we can compare with a reference station as well. And we can even do statistical comparison and hypothesis test between that reference and our TMDL watersheds. Again, same cautions for small data sets would apply. Again, we can look at habitat data in comparison to the stressor probability thresholds. But we also want to take a look not just at total values, but the individual metrics, because those different metrics may tell us some different things. And here I've kind of color-coded a couple, well, two different things that metrics are telling us. One in green are some sediment indicators. The metric of embeddedness and sediment are two pretty good indicators that can tell us whether sediment enrichment is an issue in stream, in the stream substrate. But then some of the others, which are highlighted in blue, they give us, again, what we can call contributing factors. Okay, so things like alteration and bank vegetation, riparian vegetation, those actually aren't telling us what the conditions of the in-stream sediment is like. They're telling us what's happening up on the banks. Now, obviously, the two are related. If we have actively eroding banks, we're going to also probably have in-stream sediment conditions as well. But maybe not, and it might depend on the location as well, because poor riparian areas at one portion of the stream might actually lead to downstream in-stream sediment issues. And so there's a spatial component there as well. But I would encourage you to look at, particularly for sediment, look at the embeddedness scores and the sediment scores, compare those with a reference, but then also look at those, basically those riparian scores, because they're going to tell you, is there an active source of that sediment? And when we later begin to talk about causal analysis, here we're beginning to link causes to effects, right? The cause might be poor riparian vegetation. Well, that's leading to active erosion, which is then leading to an in-stream sediment condition. And so we're beginning, even through these individual habitat metrics, we're beginning to link some sources with some impacts and effects. The relative bed stability analysis is another useful tool for us in evaluating habitat. What the relative bed stability analysis does is it takes a number of different measurements, pretty intensive, not just at one location, but across a stream reach. And within that stream reach, what the approach is looking for is basically the ratio of the observed sediment size that we see in the stream to what would be predicted based on the bank full depth and other channel dimensions. So it's basically a measure of how much sediment should this stream be carrying compared to how much it appears to be carrying. And large negative numbers of the log relative bed stability value, those large negative numbers indicate instability and the possibility of excess sediment deposition. Large positive numbers, which we don't see that often, are an indicator that maybe this stream is sediment deprived. Maybe it needs more sediment. In looking at relative bed stability data, don't forget the other measures that are there. Okay, we end up with kind of the final ultimate score of a log relative stability index, but also there's great information there on percent sands and fines, percent embeddedness. And keep in mind that for our visual habitat assessment, we're doing an assessment of embeddedness, right? Well, that's one time, one place. The relative bed stability analysis is a much more intensive and quantitative measure of that same embeddedness. So together, the two provide us with much more information. So don't forget to look at that data as well. A few caveats about relative bed stability analysis. Just as I said that the benthic stressor tool is not in and of itself the stressor analysis, it's a piece of it, it's one line of evidence. I would say the same about relative bed stability. It is one measure, okay, and it's one line of evidence. I don't think it's a yes or no whether sediment is a stressor or not. We need to look at it within the context of our other lines of evidence as well. Some limitations. It was validated as a regional measurement. I think it's most accurate with repeated visits. And I think there's some questions too as to the impact of large scouring flood events. In the North Fork Rivanna, we had the opportunity to have 3 different measurements of relative bed stability within at the same location over time. And those numbers increased as flow increased. And particularly after a large flooding event, those scores were much better actually. Well, why would that be the case? Well, a large scouring event is going to remove sediment from the stream. And if we do that bed stability analysis after that scouring event, it's going to look like, well, the stream isn't holding as much sediment as maybe it did a month ago before this particular scouring event. So I think there's some timing elements that can influence the relative bed stability measure. I think there's also some questions in urban environments. I'm not sure if it was well validated in urban environments, and there's so many channel modifications within the urban landscape that, first of all, it's very difficult to tell sometimes what bankful depths are. And so I think there's a lot of variability in what that bankful measurement is within an urban environment. And I think in an urban environment, because the hydrology is changing so quickly, that I think that that bankful depth is actually a moving target. And I think that typically these particular urban streams, they're in a process of expanding, widening, and deepening. And so I think oftentimes it's very difficult to tell what that bankful height is. And I think it may be steadily and progressively changing over time as well to adapt to its new hydrology from all of the imperviousness of the area. All right, time to check in again. If you have questions, go ahead and write those in the questions box, and we can deal with them now.
Hey, Robert, we already have one question from a few minutes ago. I know we talk mostly about temperature, sediment, pH, et cetera, but how does bacteria affect these benthic communities? Is that ever used as an indicator?
I really don't look at bacteria data much in the benthic stressor analysis. The bacteria information that we collect is either total fecal coliforms or E. coli. Those are both indicators of fecal matter from warm-blooded animals, humans, livestock, wildlife. There's not much evidence that those bacteria have an impact on benthic macroinvertebrates. So I have not used that in the past as any indicator. Now, there's probably some correlations with those bacteria numbers as you have more nutrients and more sediment. If that's coming from the agricultural landscape, you're probably going to have higher bacteria numbers and bacteria levels as well. So there's probably some correlations between parameters, but I don't think there's any direct causal impacts from the bacteria, at least from E. coli and warm-blooded fecal bacteria.
Okay, great. Next question. How do PCBs affect benthics, especially in the lower background levels we see in streams?
Ooh, good question. Typically, I think the best value to compare with is there was a study by McDonald et al. I think it was 2008. I might be wrong on the date, but they developed what they called consensus sediment criteria. And so that was done for a number of metals as well as organic pollutants, including PCBs. And what they did was looking at a lot of different literature on toxicity thresholds for those contaminants came up with what they thought would be threshold levels of impacts in the sediment. And so if you have sediment PCB values, you can compare those with those particular thresholds. And one thing I like about the McDonald thresholds is they provide two different thresholds. One is a probable effects level, meaning if you see values above that, you're likely to see in-stream impacts on the benthic community. Then they also provided a lower threshold level that if you see values less than that, you're not likely to see impacts within the stream. And so of course that leaves you with a zone in the middle where maybe you do and maybe you don't. But I think by providing kind of an upper and a lower threshold boundary, that helps you in some cases decide whether PCBs might, and other metals and organics might be an issue to the benthic community as well. But yes, those contaminants can be toxic to benthics, just like they can to the humans and fish as well.
Okay, great. We'll be sure to capture that McDonald reference in the references document that accompanies the recording. Next question. What is considered a small data set for water quality data and benthic data for the stressor analysis?
Oh, it's tough to put an exact number on what's small. I'll tell you, large is probably over 100. Over 100 data points is a large data set for a particular parameter, particular location. Under 20 is definitely small. So again, between 20 and 100, is it small? It might depend on the parameter. What's its distribution throughout the seasons and over time? But I would be a little careful with data sets, less than 20 data points.
Okay. Next question. Wouldn't a high flow scouring event just move the deposit sediments downstream from your sample station? Do we account for that or just assume it's gone?
Well, most of your high flow events are actually going to take sediment out of the stream channel and they're going to deposit it on the floodplain. And so once the stream makes its way back into its original channel, that sediment may not be there anymore because it's, quarter-inch thick over, 100 meters or 100 feet away from the stream. And so you see this in areas, as you go out to floodplains, you'll see, all the grasses that have been laid down by the flood, they're covered with sediment. And that's the natural approach of streams is to take sediment and take it from the channel and up and deposit it on the floodplain. Many of our streams, if they're too badly incised, they're not able to access their floodplain, which causes some sediment issues with smaller frequency floods. But for our large scouring events, typically that sediment, obviously, a large portion will be moved downstream, but a large portion is deposited on the floodplain as well.
Okay, great. Couple more quick questions, I think, or maybe not quick. We often have abundant benthic and habitat data for reference sites, but more limited water quality data. Do you think having ambient water quality data at benthic reference sites is of equal importance?
Yeah, I think so. Obviously, you've very rarely ever heard somebody say, "Wow, boy, I wish we didn't have so much data." Usually the issue is, and particularly with TMDLs, a lot of times you get into the TMDL and your comment is, "Boy, I wish we had X, or I wish we had more data. Wish we had more data here, or wish we had this type of data here." So, yeah, the more data we can find it in a perfect world, you would love to have a benthic station with a long history of benthic data that's co-located with a long history of water quality data that's also at a USGS gauging station. So that's the perfect setting, right? Obviously, we don't always have that, and we work with the data that we do have. But yes, the more we can co-locate those stations. And sometimes maybe it's not necessary to have them completely co-located, but if they're within, several miles of each other, and there's no major influences between them, then you can consider that just as good.
Okay, and as a follow-up to that, do you think it's important enough to consider establishing routine ambient monitoring stations that commonly use benthic reference sites?
I'm sure there's some of that that's being done already, but I think it'd be a consideration where it makes sense.
Okay, great.